So, the title of my talk is Nonlinear N-term approximation in two types of spaces, HP, Hardy space, for P between 0 and infinity, and the second type of space is BMO. Both of them are living on the sphere, and I'm going to approximate with shifts of the Newtonian kernel. I'll explain a little bit later the approximation tool. And what I'm going to compare actually is the actions of these approximation theorems in both HP and BMO. They're not exactly the same, so there are differences which I'm going to explain. All these are results which are obtained in cooperation with Penchuk-Petrushev. Okay, so how to end of the talk? First, I'm going to speak about separable spaces, which are HP, and after that about non-separable spaces, which are BMO, not VMO. VMO is separable space, but actually the difference between separability and non-separability makes the difference between the approximation in the two places. And at the end, I'll say something about Bernstein-type inequalities, say something. Otherwise, everything else is about Jackson-type theorems, direct theorems. First, results for separable spaces. What about the domain? From one side, I'm going to consider the unit ball BD in the RD space for dimensions bigger or equal to 2. In this ball, we have harmonic functions which are going to approximate, and they exist very well in the domain BD. Next, going to the sphere, which is the boundary. From one side, I'm going to consider the sphere in dimension 2, which is the circle. On the circle, we approximate by trigonometric polynomials. What is important, the group of translations on the circle is commutative, so we have abelian harmonic analysis. This is for dimension d equal to 2, but I'm going to consider all dimensions, nature, d bigger or equal to 2. So next one is the real sphere, starting with dimension 3 and up. So in this case, we approximate by spherical harmonics. The group of translations is not commutative, unfortunately, and the life is more difficult. So we have non-abelian harmonic analysis. The idea for doing approximation on the sphere actually comes from doing approximation in the whole space RD, where we have a very well-developed theory for the group of translations here, of course, is the simple translation, which is commutative, so the life is a lot easier having abelian harmonic analysis. So, from the point of view of the domains, the main difficulty is coming here, starting with dimension 3 or higher on the sphere. Now, function spaces. I'm going to define the function spaces starting with H of BD, which means the set of all harmonic functions in the open unit ball. After that, HK will denote the space of all spherical harmonics of degree k on the sphere. The dimension of HK is well known. Here it is. What is important that for different Ks, all HKs are orthogonal, and L2 can be represented as a direct sum of HK. In every such space, HK of spherical harmonics, so many spherical harmonics, we can take a real valued orthonormal basis, denoted here by YK nu. K is the same as here for HK, and nu is the number inside. It doesn't matter how well, in what manner you have defined this orthonormal basis. Any ordering will do the same job. So, the harmonic coefficients of any function u, which is harmonic in the unit ball, can be defined in this manner. we have here the orthonormal basis, the function u, and we take an integral on the sphere, but a little bit inside the domain. We go a little bit inside. Okay. These are the coefficients of the function u according to this basis as it's written here in the bottom. What is important that this coefficient does not depend on the parameter a. This is how much you shrink and go inside in order to write down the coefficients. Any a between 0 and 1 will do the job. And at least formally, we can write the harmonic function in this way. The value of the function at distance r from the beginning and sees the direction on the sphere, here there, can be written in this series. Now, about the convergence of the series on the next slide. And moreover, the same series as it is here, but Rk is taken in front of the inner sum. We can, we can write also the operator j to the power beta by using these multipliers which are written here, k plus 1 to the power beta, otherwise the series is the same. So, usually this is called Weyl derivative whenever b is positive. If I'm not mistaken, yes. So, when beta is 0, we have the identity here, and this series for any beta converge absolutely and uniformly on every compact subset of the unit ball. So, this is also a well-defined harmonic function. Having defined the derivatives and integrals altogether with this beta, we have the definition of harmonic Bessel space written in this manner here. Given parameter S, which is going to be for smoothness always, main parameter, smoothness parameter, and two parameters P and Q between 0 and infinity, including infinity. And let we put beta equal to S plus 1. This is the standard thing, harmonic Bessel space. B, S, Q, P is defined as the set of all functions U, harmonic, for which this norm here is finite. We have the beta derivative of the function u, take the norm in LP on the boundary, and after that take the LQ norm of this expression here on the radius, in the radius direction. Whenever q is equal to infinity, we have simply the supremum here, which is Bs infinity P space. Now, these are Bessel spaces. They are defined from the behavior of the harmonic function inside the unit ball. Now, next slide will be triple Résorquin spaces. It's almost the same. Just LP norm and LQ norms are interchanged. So LQ norm goes inside, LP norm goes outside. Here they are. So with F, S, Q, P, we denote triple Résorquin spaces, where inside we have LQ norm and outside LP norm. This is the only difference. Triple Résorquin and Bessel spaces are very similar, but there are some small differences, and we'll come a little bit later to such kind of differences. About the parameter beta. Doesn't matter how big it is, still to be bigger than S, bigger than the smoothness. Any beta will go and give you the same equivalent quasi-norms. Why quasi-norms? Because both P or Q can be less than 1. When P and Q are bigger than 1, we have Banach spaces, not quasi-Banach spaces. So you have the pure triangle inequality with these norms. Okay? And finally, the space where we are going to do approximation, Hardy space, HP for P between 0 and infinity is defined with this expression here. Inside the P norm and OP norm on the sphere. You have the radial maximal function of the function u. You take the supremum on R between 0 and 1 inside, and after that take the LP norm on the sphere. You may take other types of maximal functions here, which are well known, but this is enough for our definition. Now, some special cases and why we're considering all these different types of spaces. First thing, whenever P is equal Q, here we go, Besu spaces and Hardy spaces coincide with equivalent norms. Oh, trivial resorting, sorry, trivial resorting. And Besu spaces coincide, thank you. For Q different than P, they are different spaces. Okay. More or less, trivial resorting spaces looks more as a function spaces, and Hardy Besu spaces looks more as coefficient spaces. But this is only partial explanation, and I'll give you also other examples after that. And we need trivial resorting spaces because of this one thing here written in the bottom. The Hardy space is actually a trivial resorting space when the smoothness is 0, and the second smoothness parameter Q, the fine-tuning of the smoothness is equal to 2. So in this case, Hardy spaces and trivial resorting spaces with this specific small choice of smoothness parameters coincide.
So if P and Q equal 2, do you have just a characterization from the harmonic coefficient of these norms? For the Hilbert space, for P and Q equal 2, then
yeah. Yes, we go to Hilbert space. Yes.
And but then is there can you express the norm in terms of the coefficient of the basis that you as a weighted sum of the coefficients in this basis?
I'm not sure. Equivalence, yes, but equality is Besu inequality. I'm not sure. The equivalent. Yeah. P equals 2.
For higher smoothness. You think of this space to be smoothness condition for the functions on the sphere in a way.
Yeah, this is like
okay. So I'm going to approximate in Hardy spaces in the beginning with functions from Besu spaces, or which is the same with trivial resorting spaces for this special choice here of the parameters. And this is inside the sphere. Now, in order to prove the necessary results, I'm going to go on the sphere now to show the counterparts of all these spaces on the sphere. Here we go. Now, we go to spaces, these types of distributions on the sphere. They are going to be also functions, but in general, they are distributions. Let me recall y k nu to be the real valued orthonormal basis. Then the kernel of the orthogonal projector on the space of spherical harmonic, of degree k, is this one here written with zk. Okay. Test functions are all infinitely differentiable functions. We're on a compact set, so no need to assume additional compactness as in Rd. So these are the test functions, and respectively the continuous linear function also on S form the space of distributions S prime. For any distribution, for any continuous linear function now, we define the convolution with the kernel of the orthogonal projector in the standard way. Here we go. This fat dot here is the integral of the same variable as in f. Okay? And now the standard definition, which goes back to Petre. We take a number b bigger than 1. I'll explain later when I'm writing b here instead of the standard thing b equal to 2. And take an infinitely differentiable function on R plus, support it in b to the power minus 1b, and strictly positive inside the interval, b to the power minus 1 half, b to the power 1 half, separated from 0 by a positive constant inside. So these are the general conditions of the function phi. Then, for the given distribution f, I define the following convolutions, similar to this one here. These expressions are coming here. Simply for the different case, which range in this interval here, where the function phi is non-zero in the support, we make this sum here. So, this is the standard construction in the needless switch bench we like very much. And we have the first definition of the Besov and Triboel-Lizorkin spaces. We take the norms on the sphere of these expressions, multiply to the b to the power sj, j is the same here and here, and take the sequence LQ norm of this expression. This is the Besov space on the sphere. Once more, if you interchange the LP and LQ norm here in the bottom, we have Triboel-Lizorkin space. Okay, both of these are spaces of distributions, and for some parameters, they also, when the smoothness is enough, you have spaces of functions. One specific difference. This is defined, the Besov space is defined for p less or equal to infinity. Triboel-Lizorkin space is defined in this manner for p less than infinity. Whenever here p goes to infinity, is equal to infinity, we have a separate definition which goes to BMO in the second part of the talk. Now, doesn't matter how big is b bigger than 1 and what is the function phi, well, they always generate the same spaces with equivalent norms, so these definitions does not depend on the function phi and the parameter b. Okay, now some more properties. When you're on the sphere and p is strictly between 1 and infinity, the Triboel-Lizorkin space with S smoothness equal to 0 and second fine smoothness Q equal to 2 coincide with the LP space. Similarly, for on the ball, the Triboel-Lizorkin space 0 to p coincide with Hardy space for p between 0 and infinity. Okay, and something important, what happens with so many parameters. I'm not going to give you all possible embeddings, but only these partial embeddings. Take some p, q is smaller than p, r is bigger than p. This is for the smoothness parameter q, which is upstairs. Second, s and p here always keep one and the same. So for q equal to p, we have the same spaces here as before, I told you. After that, when we take r bigger than p, we have that Triboel-Lizorkin spaces are embedded into Besov spaces. When r is going smaller than p, q, that is q, we have that Besov spaces are embedded in Triboel-Lizorkin spaces. So in a sense, Triboel-Lizorkin spaces are closer to each other than Besov spaces with the same values of parameters. Now, all these embeddings are strict you do not have coincidences here under these values of the parameters. So from one side, we have trivial Zorkin spaces for P equal to Besson spaces for the same P. On the other side, trivial Zorkin space for 2 equals to the standard spaces which do exist. Okay? And finally, some connection between trivial Zorkin spaces on the sphere and on the ball. Take any harmonic function, and let these numbers be the harmonic coefficients. And they have no more than polynomial growth at infinity. This means supremum on nu, and after that as a function of k going up to with a polynomial order to infinity. Actually, they will go usually down with good smoothness, not to infinity, but to 0, but doesn't matter. This is upper bound. Okay. For every such harmonic coefficients, we have a distribution on the boundary defined formally with this series. We have convergences in S prime, and we can give the following theorems. A harmonic function from the trivial Zorkin space, f, s, q, p, all parameters given there, belongs to this space if and only if its boundary value distribution, defined by this formula, belongs to the corresponding trivial Zorkin spaces on the sphere with equivalent norms. And also for the Besson spaces, a harmonic function belongs to the Besson space on the ball if and only if the corresponding boundary distribution belongs to the Besson space with the same parameters on the sphere. So we can go easily from sphere to the ball and back without having any troubles on this place here. Now I'm trying to, I'll recall you that this norm here was defined in a pure terms of the behavior of the function inside the sphere, in the ball. And this definition here of the space was with the behavior of the function on the ball. So, in this respect, there is no tautology going to repeat one and the same things. These are normal equivalence theorems.
Is this proved through maximal functions?
We have p less than infinity. Now, I have the spaces in which I'm going to approximate and the spaces which will define my smoothness, some. So, what I'm going to approximate with? I'm going to approximate from shifts of the Newtonian kernel. What is the Newtonian kernel? For dimension d bigger than 2, 1 over the x minus y in Euclidean norm to the power d minus 2 is the Newtonian kernel. Whenever the dimension d is equal to 2, it's logarithm of the same, of the first power of this. This is the Newtonian kernel. And these functions here represent harmonic functions inside the unit ball and also on the unit ball, provided all balls y nu, which are written here, are bigger than 1 outside of the unit ball. Then they can be very close to 1, actually, but they are supposed to stay out of the 1. So we have in this definition here 2n plus 1 parameters, a0 and nu are coefficients, complex numbers, and the poles here. Now, not only the coefficients a and nu can vary, but the points y and nu also can vary. So we are in non-linear case. when we add two functions, we're going to get another function of the same type, but it is going to be n with index 2n. No, we cannot, this is not a linear space. Many people have approximated with such kind of functions with one very big restrictions. They always took these points, the poles, to be fixed. So they say, let me put the points here, 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 and after that we're trying to approximate, which more or less makes the problem linear. In this problem, the poles are free to go everywhere outside of the unit circle. Okay, this is not compact, but doesn't matter, we'll survive. So, Jackson type theorem on the ball. First, we define the best approximation of a function f. With the element of this space is n with parameter n, the shifts of the n shifts of the Newtonian kernel, by standard way, where B is some kind of Banach space, doesn't matter what. Okay. First theorem. Take any dimension bigger or equal to p between 0 and infinity, and the smoothness S to be positive. For every function f, which is in the Bestor space with parameters s, tau, tau, which is the same as the Triboel-Zorki space, and the standard connection with the parameter 1 over tau is s divided by d minus 1 and plus 1 over p. We have the following Jackson type theorem. The best approximation is n to the power minus s over the dimension of norm of the function in the Bestor space. Now, I said n to the power minus s over the dimension. No, it's a dimension. You live in RD, but you have harmonic functions on the ball, and so they're actually, because they're equivalent to what happens on the sphere, they have dimension d minus 1. So I did not mistake. Actually, the space of harmonic functions has this dimension d minus 1. So this is the standard Jackson type theorem for functions which are defined in the unit, inside the unit circle, harmonic functions. This is the Hardy space here, between 0 and infinity, and counterparts on the sphere. Now, best approximation of the Hardy space, the same theorem as before, but these are the spaces on the sphere here. And also, for OQ, between 0 and infinity, if you take approximation on the Triboel-Zorki space on the sphere, from the left-hand side, it's the same theorem. Okay.
So the two theorems are essentially equivalent?
Yes, the two disappeared from here. Okay, now, but this is for the Triboel-Zorki space. This is not the same for Bestor space, if you put it in the bottom. So, for the Bestor space, you also have such kind of Jackson type inequality, but only for Q bigger or equal to P. When you go down for Q between tau and P, tau is here, it's given, you also have similar Jackson type estimate, but the order here is not optimal, this optimal order here. It is going to be something smaller. And so, Q bigger than P, Q smaller than P, but bigger or equal to tau. And whenever Q goes smaller than tau, you don't have even embedding of the corresponding of this Bestor space in the other one. So you cannot have approximation. So, this is one story for the Triboel-Zorki space to approximate these spaces, and a different story too for the Bestor spaces. They have different behavior. Usually the people finish up to here, going to approximation in Hardy spaces, and that's it, or LP if you prefer. But here we have studied the behavior for the other values of the parameters, not only when Triple-Lisowski space equals to HP. Okay? Now I'm going to move to the case where P is equal to infinity for the Triple-Lisowski spaces. For the Bessu spaces, they are defined there. We cannot say many things there. And let me go a little bit back here. The wife here is not very interesting because P bigger P is whenever P is equal to infinity, we have nobody here, so there is no such kind of theorem here. Okay, BMO, bounded mean oscillation on the sphere is defined the set of all integrable functions f which deviate from the average on the ball in the absolute value and divided by the measure of the ball by a finite number, which is called the norm in BMO. Now, sigma is the Lebesgue measure on the sphere, so nothing special here. Average of f on B, I think this is self-explanatory. The measure of the ball B, and we're taking a supremum over all balls.
Excuse me, so you intersect the sphere with the ball and you take the measure of this little piece?
No, actually, the spherical cap.
The spherical cap.
Yeah,
so it's
spherical
really the spherical cap that you...
Yes, center on the sphere.
Sure. Okay.
Okay, so, thank you. These are the spherical caps.
Yeah.
Center X on the sphere, and radius, whatever it is. We have John Nirenberg inequality, which gives us that there is nothing special here with the L1 norm which I have taken. I can take any LQ norm, Q between 1 and infinity, and still to have something equivalent to the BMO norm. So for Q bigger than 1, we'll have the same as the BMO norm equivalent to a constant. Q is less than infinity. In fact, something like this, we're not going to use it. It's true for Q between 0 and 1, but you cannot take average here. You have to take infimum, best approximation with constants. Because for Q, if you take the function to be, for Q less than 1, you don't have averages. Okay, so we have BMO and equivalent norm in BMO. Oh, here it is. Now, BMO is something very close to L infinity, but it is not L infinity. In fact, L infinity is embedded in BMO, but it is not equal. And the most important example is the logarithm of absolute value of x minus xc. Both x and c belong to the unit sphere. Say xc is fixed, x is running on the sphere. This function here belongs to BMO, but it is not obviously in L infinity. So this is the typical example. So we have more functions, a lot more functions than in L infinity. VMO, vanishing mean oscillation. It is the same as BMO with this difference in the red here. We're not taking all balls, but balls with radius less than delta. And take the limit for delta going to 0. The other expression is the same. And we would like to have here 0. These are the functions of vanishing mean oscillation on the sphere. Now, for those of you which have worked with vanishing mean oscillation on the RD, it's a little bit different. You have more conditions there. But on the sphere, this condition is the only one which has to be imposed on the bounded mean oscillation functions in order to get vanishing mean oscillation functions. VMO is equipped with the same norm as BMO. Properties. Both of them are Banach spaces, provided you have identified two functions which differ by a constant. So you have to have classes of equivalence because any constant will. But whenever you do this, you have Banach spaces. VMO is a closed subspace of BMO. What is important? BMO is the closure of C infinity functions, the test functions, in the BMO norm. Okay? And the biggest difference, VMO is a separable space, while BMO is not a separable space. Listen, when you are going to make approximation with n terms by something which is it could be manifold, but it's a fixed number, given number of parameters. You cannot do approximation in a non-separable space. You have to have separable space where to live. It is the same as, in this respect, as approximating in L infinity or in C, in a given interval. In continuous functions, you can approximate. L infinity functions, you cannot approximate by such kind of families. So the L infinity is not a separable space. C is a separable space. We have the same here. So I have put blue and red colors for this part of the statements. The colors has nothing to do with the understanding of the colors in the United States politics. These are different. Okay. Now, triple Kozlowski spaces, when p is equal to infinity here. Other parameters are the same. Okay, here it is p equal to infinity. It is a little bit different than before. We have something 1 over b integral over b for any ball which has a radius r and center somewhere on the sphere. But we take this expression which stays for the Kozlowski spaces before, starting from some place after that. So, roughly speaking, the frequencies which are higher than the frequency of the which can be bared by this ball. This is the most important part here. When you take such kind of things, for whenever q goes to infinity, so this is for q less than infinity, for q equals to infinity, this is a simple definition which coincides with the best of norm for these two parameters, but this is not going to be interesting for us. Okay, we have triple Kozlowski spaces defined in this way. Now, the best triple Kozlowski spaces are going to, these are non-separable spaces. It will be written somewhere after that. And we will need separable triple Kozlowski spaces. I have put 0 at the top of the F here. In addition, we would like to have similarly to the VMO, the limits for delta going to 0 of this expression where the radius is bounded from above by delta is also going to 0. So in this way, we have separable triple Kozlowski spaces about the name separable. On the next slide, I guess, or in this one I have forgotten. Oh, here we go. Parameters 0 and 2, you get BMO. Parameters 0 and 2 here for the separable triple Kozlowski space, you get VMO. Okay, too many spaces. Theorems. Jackson type theorems. Let we take S positive and 1 over tau equal to S over d minus 1, the dimension. Plus 1 over p, but p is infinity, so it's 0 here. There is no more. If the function f belongs to the corresponding Bessel space, then we have This order, the same order of the best approximation, nonlinear, in the space BMO by shifts of the Newtonian and shifts of the Newtonian kernel. And similarly, let me see, not only for BMO, but for all triple Shortkin spaces. Here we go. We have 0, 2. So the other Q equal to 2 in the next slide. Okay. We have taken this one. So this is the generalization in this sense of the previous theorem. Okay, now, something about the proof. Sketch of the proof, it is not going to be the proof, we are far away from it. First, in order to work in BMO, we need some kind of nested structure, I will explain. There is no need for such kind of nested structure when you work in HP, P less than infinity. But this is analog for P equal to infinity. We have to make some kind of nested structure. Now, this nested structure is going to be similar to the dyadic cubes in RD. We have a multi-level collections of open sets. Now, the Q is the open set, C is the index. The index is running from level sets Xn and going to 0, from 0 to infinity. Actually, Xn are points on the sphere. The disk C in Xn are point of on the sphere which are distance between each other to the distance 1 over n. Sorry, 2 to the power minus n, excuse me. Different points on the sphere. For Xn, fix n is a level. The sets in every level. They're disjoint, these Q's are disjoint. They cover the whole sphere up to a set of measures 0, which is not important. And the measures of any two sets on the same level are equivalent. That is the ratio of the their measures is between two absolute constants, which does not depend on n2. And every set is a subset to a set from the previous level, the parent set. Also, every set has at least two children. At least two children. Now, this is explanation. How many sets, roughly speaking, we have on a given level n. This is b to the power n times d minus 1. This is easy. And now, why I need this number b in the beginning? Not going to the steps 2 to the power n in the definitions, but b to the power n. Now, I have to ensure such kind of structure here, nested structure. And such kind of nested structure exists always if b is bigger or equal to 4, not to 2. In fact, all what is written here exists for b bigger than 3, except the only condition, every set has two children, at least two children. To ensure two children, you have to go to b bigger or equal to 4.
You say you have to, or this is your proof?
This is the proof.
Yeah.
This is the
Maybe
proof.
somebody more
Actually,
clever will come up.
Actually, this is not my proof. I'll give a reference a little bit later. Okay, so now, think a little bit. You have a sphere. You have a net on the sphere of points which are, roughly speaking, 2 to the power minus n to the distance to each other. This is one level. Going to the next level, 2 to the power minus n minus 1 difference. But you don't know how the points are distributed. You have to see that how open set in one point goes in the open set in the upper level as an inclusion. This is the problem which exists here. So there are wiser guys than me which have solved it, but this is what follows from the proof. Okay, we have done such kind of nested structure.
Does this add SAF from these people, or different?
No.
Who are these people?
I've have a little bit. I have the name after that.
Michael Chris.
Okay.
Oh, Michael.
Chris, yes, Chris.
Right.
Christ, okay.
Christ.
Yes.
Your name is Christ. You should be able to know it, right?
After that, for all these spaces of trivial Zorkin type, FSQ infinity, and the homogeneous, the separable spaces, we are constructing a needlet frame decomposition. C is the frame, the dual frame is psi tilde. Okay, with this property here, you can represent every function f on the with distribution with this formula, and you have also equivalent norms of the function norm here, which I have written, and the sequence norm of the corresponding sequence space. So you can go back and forth from the function space to the sequence space. And also all frames of this needlet frame, the composition are needlets. Needlets means polynomials. Okay, having such kind of needlet frame decomposition, we built another decomposition, Newtonian kernel frame decomposition. I haven't tried to write down because it will happen something with the slide of Olga to have too many things on the screen here. Okay. Anyway, we have similar decomposition of frame, dual frame, only for the separable trivial Zorkin space, not for the whole trivial Zorkin space which correspond to BMO, with these properties here, the same as before, but the needlets are replaced here by Newtonian kernels, where every frame element is a linear combination, a fixed number of translations of the Newtonian kernel. Fixed numbers means that they're one and the same number independent of the level. So for every level you have 1 million, for example, such kind of translations. Now, what is important? We have also the same frame decomposition for the Bessel spaces, which stays in the theorem. Actually, for all Bessel spaces for p between 0 and infinity. The same thing is a frame there. Okay, next step. We're doing the n-term nonlinear approximation in the sequence space. I have written something which is a norm in the sequence space. Now, this is the nested multi-level structure. You take a point C, which is in the same time index set, index. You take all open sets which are inside this open set of this point. Take the HQ norm, but you have the additional factor, which is the area of the smaller the set inside divided by the area of the original point C also. So such kind of norm which is necessarily working with embeddings of the different levels, and we prove the corresponding sequence type Jackson inequality. Here it is. And what is the sequence type inequalities for LP, which are working, or HP, are a lot easier than the sequence type Jackson inequality here. The proof is essentially more complex. Okay, and finally, combining all this, you get nonlinear n-term approximation for separable trivial Zorkin space. You take start from the separable space, take the coefficients and going to the sequence space, approximating the sequence space, go to with approximation in the L tau sequence space, which corresponds to the Bessel space, and go back to the Bessel space, and you get the theorem. Okay, so this is a rather long program, but it works. Okay, several notes from the bottom. Nested structures on the spaces of homogeneous type, including on the sphere, are studied by Michael Christ. Oh, Christ. Okay, he is in the bottom. You asked me. Okay, BMO is studied in the work of Kozani, 1985. Newtonian kernel frame decomposition of the separable trivial result in space is also a new result, not only the Jason type results. Now, let me go up in the notes. All these results naturally extends to approximation of harmonic functions on the ball. I haven't written the theorems, it would be too much. Now, needed frame decomposition of Bessemer trivial result in spaces on the sphere borrows ideas from the phi transform of Michael Fraser and Javert. Now, in next slide, this definition here is similar to the definitions of Fraser and Javert, but not to the definition of trivial of the same type of space. Trivial gives another definition where he uses Fourier transform, but I have tried to explain you that whenever you are on RD, you in the abelian case, you have a very, for example, Fourier transform, you can do the life is a lot easier than going on the sphere where, except for the case d equal to 2, otherwise all spaces are non-abelian, so you cannot play so easy with the translation on the sphere. Okay, so we have taken from where the definitions are coming. Okay, next. Bernstein type inequality. Two slides which are very easy. It is easy to prove, with question mark easy, but it doesn't matter. This Bernstein type inequality with the following specific things. Here, every function in the Bernstein type inequality is a linear combination of the frame elements of the translation of the Newtonian kernels. These are theta's here. Now, when we go with n number, so this can be done. Big open question, conjecture, okay, we have put it. Can you prove Bernstein type inequality when you take the more general sets here of functions which has only n poles outside of the unit circle, but they're otherwise arbitrarily distributed? What is the difference? Here, all these objects are very well localized, so you can play the game. We have combined in Newtonian kernels in such a way that we have a very well localized objects. But the original functions, from the original spaces, sets which are translates of the Newtonian kernels, the Newtonian kernel is has the worst possible localization, if any localization exists. So actually it is an open question, but to prove Bernstein theorems for HP, P less than infinity, or for BMO here, VMO actually, because all these functions from here from VMO, this is not this is obvious.
So you think this is true?
Yes, because it's written in conjecture. If it was a question, then I would not know what to think. But in this case, I think it's true. Okay, thank you. Now, I have another slide.
Oh, yeah.
Yeah.
Oh,
Now,
the centaur and their depends on.
yeah, okay. Now,
Well,
yes, we will make a quiz now. Who is who here?
so that's Andrea.
Andrei, yes.
Andrea. That's Boyan.
Yeah, Buyanov, Borislav Buyanov.
Yeah, I know.
Todor Buyanov, yeah, okay. Yeah. Okay, here's Vasil, Sandov.
Penso.
Pencho,
This is the girl.
Margarita.
Oh, that was, oh.
Margarita.
No, okay, somebody else, yeah.
Spas, Georgi Iliev, Vlado Christov, and this is myself in the bottom. Now,
That's you?
yes, that's me. Can you believe
I
it?
would never notice.
No, neither me, if I wouldn't know. Now, this is 1982. As you see,
Oh boy.
Pancho has his sunglasses.
Come on.
He has his back to the wall.
Now, but I disagree with you, Ron, today when you say, okay, he looks as a mafia guy.
Yeah.
Because you're coming from United States, so for you, mafia is something which make you think of it. From Bulgaria, on that year, we didn't have heard so many about mafia guys. Of course, we have seen the different films as Godfather, but not so much. For us, a way of thinking was, oh, this guy looks as a dictator. This is bigger than mafia. Now, can you recall which dictators I have in mind? Two, which were with sunglasses on that time.
Oh, Gaddafi?
No. He was not so popular in Bulgaria.
Zhivkov?
No. One was Pinochet. Yeah, but before that actually. But exactly
He was a murderer and he was a terrible
exactly
guy.
on exactly on that time, which is a very important. I am not saying popular, but important dictator in socialist countries was another general, Jaruzelski. No, Jaruzelski in Poland. He has just made the translation of powers in Poland. So we were teasing on that time, Pencho, that he looks as Jaruzelski.
Fidel Castro too, right? Didn't he have some sunglasses?
I cannot remember.
Very nice.
Very good picture.
Bulgarian mafia.
Unfortunately, Wolfgang, I was not able to find you on this picture, but that's it.
That was the year 80.
82. Yes.
So when did I came to Bulgaria was in 84.
And then that,
After that.
after that, 80.
I was in 84.
86, 85, 86, or 86, one of these, yes. Yeah. Okay, this is what I was able to find for Pencho.
Well, it was nice. I mean, Bulgaria had a very strong tradition, and approximation was very strong. And then it got dissipated, I guess, by the...
You attracted Bulgarians to
Yeah.
South
You lost is our game,
That's
right?
called brain drain.
Yeah.
Okay, thank
Here's
you.
a question about your talk.
Hmm?
Can you send me that picture?
Yes. Okay. Yes.
There's a question about your talk. What happens if you interpolate between Bessoff and Tribble-Zorkin in your setting? Do you get Bessoff? Or
no.
no?
Whenever you interpolate the
Or this way, yeah, but
no, the
I want to
angle.
nonlinear.
Yes,
Yeah.
no linear interpolations. You got, if in both sides you have Tribble-Zorkins, inside you have also Tribble-Zorkin. If you have in both sides Besso spaces, inside you get Besso spaces. Coincidence, you have coincidence only when P is equal to Q.
But you get what you expect.
Yes, otherwise, what is if in one
this
side
is
you
all
have
true.
Besso and in the other Tribble-Zorkin, I don't know.
This was proved by you guys, or who proved this?
The interpolation falls relatively easy, what I'm saying. We have a lot of...
P less than, if P is less than 1, it's not so easy to do.
It's terrible to work in P less than 1, I know.
But anyway, it's no, you guys.
Yes, but don't forget that more or less you go here to sequence spaces, which a little bit make the life easier.
How do all these spaces I'm forgetting compare with, to get the other approach to get bits of spaces on manifold is through mapping, I mean, for local coordinates and just using the Euclidean
Modular.
definition. I mean, so I mean, there's a whole book by Johnson and on bits of spaces on domains, and so.
Siegel defined these things.
Yeah, so that it essentially coincides with what you do.
Yeah, but not for all indices. This is like little period and comparison with classical.
Yeah.
You could take also this figure Chisielski.
Yeah.
Not charts, but it's decomposition.
But exactly what's the relationship I cannot see.
So this is typical potential U type. For most human beings, they see this and they say, let's try something else. We'll do something else. I mean, you know, why do we want to be so miserable the rest of our lifetime doing this? But
I would agree with you that this is not humane, but
this puts hair on your chest.
no, but otherwise, the result, I like the result.
No, but I mean, there
No,
is
it's nice that it's
motivations
not.
for approximation by Newtonian potential.
Oh yeah, I think that's a very nice idea. Can you do this adaptively? The Newtonian? I mean, working on,
No,
getting closer and closer to this.
But it's almost.
Listen, this is the best possible actually. When how the work, how the approximation is done.
Yeah, I'm saying like for free knot splines, we never do it. I mean, you never do free knot splines. You can't find the spacing of piecewise, where breakpoints and all that. So you do it adaptively, you almost get the same result. I'm wondering, is it, in this case, do you have it organized in such a way? Can you do it adaptively?
No, you mean Friedel splice in LP or in L infinity?
With the Newtonian.
Well, I'm just saying in general, for example, in finite, I mean, if we're going to approximate by free knot splines, we don't do it. We instead do adaptive partitioning, which corresponds to dyadic.
Yes, something similar to dyadic, yes, where one can do the job.
But his thing is closer to wavelet in a sense. What you
Yeah,
really
yes.
do. It's really combining the Newton potential in order to obtain guides that looks like wavelets.
Here the problem is Newtonian potential. This is very hard to work. I mean, because they are not localized. So,
So this is why you have to message them
so you have to prepare, otherwise you are in trouble.
in a way you differentiate them. I mean, you
It's
do
not numerical.
differences
Numerical,
of-
you are in trouble here.
Yeah.
I mean, there is something that is called, it's related to this, by the way. In geodesy, they have the potential, and then they want to approximate it by using, putting different masses inside the ball. Inside. And question is, you have the potential, your function, on the sphere if you want, or outside, harmonic. You put inside different, move these masses. Can you approximate? And how well can you?
But they have to be positive. I mean,
They are positive, and you're in big trouble.
They are positive because your method, in fact, does not preserve this positivity. It's
No.
not
We take
guaranteed.
positive and negative.
Yeah.
But we have magnetism where you can do negative too.
Okay, that's okay.
With
Yeah.
positive, you cannot do anything only with positive.
So you need some negative.
You need a negative masses in the sense of the positive.
Yeah. This is interesting. I mean, this is a bit the same. Okay. Framing a little bit like when you approximate densities or probability distributions, mixture of Gaussians, right?
But
To think of it as close to a mixture, and the mixture has to have positive weights, right?
Yeah, but
And if you want to use your technology,
It's negative, otherwise
you,
you're in trouble.
with Gaussians, combinations of Gaussian, you have a very nice result on that, but they have to rely on putting some negative things.
That's right.
Yeah, that's interesting. And I don't know what it means from the point of view of probability then to have
This is the
negative
problem.
weights.
Same in geodesy.
But are there statements for only positive, even if they are very pessimistic?
Gravitation is always positive. This is what is for them.
No claims.
No claims, no claims, yeah.
If you restrict.
If you restrict to positive, you cannot approximate.
But you see, in geodesy they have something which is called normal gravitation, which is the gravitation of an ellipsoid, which, for example, for the Earth. They cannot achieve this normal gravitation using only positive masses. So they know this from the 19th century that, okay, they are doing it by double layer techniques. But not only with positive masses, they cannot do the normal gravity, which is the gravity of the ellipsoid, gravitational ellipsoid, which is equipotential at the same time. So they know that they have some such problems. It's a Pizzetti theory.
Very nice. Thank you.
You're welcome.